also I wanted to congratulate you for the success of the artistic project, and I've been impressed by the presentations of the people from your group and the other invited speakers. I have learned a lot, and also my students. So compliments for that. I want to talk about something a little bit different, which is flow batteries, and I believe is one of the only talks on flow batteries in this webinar series. And particularly the focus of my work over the last 3 years or so has been on how do we optimize flow battery electrodes in terms of their microstructure and their surface chemistry. And so that's the talk of today. But before I start, I wanted to briefly introduce our group. We are a new group in Eindhoven, the Technical University, established about a year ago. And we are interested in different problems in material science that are related to energy applications. And in particular, we are looking at electrochemical flow reactors. So things such as flow batteries, fuel cells, electrolyzers, and the like. And we try to use 3 tools or approaches to tackle these problems. One of them is how do we control the micro and nanostructure? So you guys have presented great work on theoretical design. For example, Sam Cooper today. And my approach has been to date a little bit more empirical or synthetic, if you will. And so I'm going to talk a little bit about that. And hopefully you see the connection between what can be done with machine learning and what can we do in the laboratory to make optimal materials. The second sort of approach that we use is we look at surface chemistry, coatings, electrocatalysts, and so on. And finally, we also spend some time in beamline. So we look at X-ray tomography microscopy, neutron imaging, and so on. And today I'm going to talk mostly about microstructure and a little bit about surface chemistry. Alejandro, can you confirm that you still see and hear me on my slides?
Yes, I confirm.
Great, thank you. Okay, so the energy problem you are all familiar with. We are going to have energy consumption continue to rise over the next 40 years, expected to double. And we need to transition to a sustainable energy system. So it's a pretty big challenge, and it cannot be solved only by, say, making sustainable the transportation sector. That accounts for about a third. But you also need to, make renewable industrial sector, electricity generation, and so on. Okay, so the good news is that renewable electricity is becoming cheaper and cheaper, but the fundamental problem is that it's intermittent and somewhat unpredictable. So now we need to find ways to store very large amounts of electricity and for very long periods of time. And that is a new challenge, which is a bit different than the transportation challenge, where you need high energy density. But here what we care about is to have low cost. Okay, so that intermittent nature of these emerging resources is calling for some sort of inexpensive and durable energy storage solution. Okay, and here there is a lot of work on techno-economics and whether lithium-ion batteries are going to make it for the grid. And I think they would have applications in the grid as well. But it's difficult to imagine that all the capacity that we're going to need for the grid will be covered by lithium-ion. And so there will be a need for other technologies. It could be, making electrochemical synthesis to hydrogen, and there would also be opportunities for large batteries. And where flow batteries actually make sense from a cost standpoint is where you go to very long durations, okay? So you can even think about seasonal storage, okay? So storing solar energy in the south of Spain over the summer and then releasing that electricity back when we need it in periods of high demand. So there are a lot of approaches these days on looking at flow batteries, and the basic premise is that they are very interesting because you can decouple the energy with the power, okay? And that is something that you cannot do with lithium-ion battery because you have a sealed compartment. But here, because you have flowing electrolyte, you could actually get higher energy just by increasing the volume at the concentration of your electrolyte. But you could also make higher power if you increase your area of your reactor. So you can play with these two, and that is something that is very interesting for the grid because you can make modular units. The problem with flow batteries is that they are currently too expensive, okay? So we need to make developments and advancements both in terms of the chemistry of the molecules, the redox molecules, but also in terms of optimizing reactor designs. So you could imagine that if you improve things on the electrolyte, you're increasing your energy density. And if you improve things in your reactor design, you are improving your power density. And actually both are important. If you look at the techno-economic theory, you want to have, small stacks and actually highly concentrated and cheap electrolytes. So the motivation of our work is currently or looking at reactor designs. So for those of you who are not familiar with flow batteries, because I assume that a lot of the audience is coming from the lithium-ion space, Redox flow batteries have the following components. So first of all, you have the electrolytes, right? Those have normally a certain solvent, which could be water, but it could also be an organic media, such as acetonitrile. You have some sort of supporting electrolyte to increase the ionic conductivity. And then you have your redox molecules. And this is an example of an inorganic vanadium species that is used in the old vanadium flow battery. But if you go to organic, this could be some sort of organic molecule. Now here is where, of course, the dissolved redox molecules are stored and then flown through the electrochemical reactor to be converted in charge and discharge mode. So now we look at the electrochemical reactor, and the electrochemical reactor looks a lot like a fuel cell or an electrolyzer. For those of you who are familiar, it's basically an arrangement of different layers of plates where you start from the outside and you have sort of backing plates and flow fields. And as you go to the inside, you start to have your porous transport layers and electrodes. And so when we look at a flow battery from the inside out, we see first that we have an ion exchange membrane. And in that case, it should be able to transport ions for electroneutrality, but it should impede the transport of active species. Otherwise, you have self-discharge of the battery. If you go now from inside out, you have these flow fields, these elements that are there to distribute the liquids. So you want to make this flow field in a way that the pressure drop is as low as possible and that you get very good liquid utilization, electrode utilization throughout. In between the flow field and the membrane, we use these porous electrodes, okay? And porous electrodes in flow batteries are something like you see here on the SEM. It's kind of a carbon fiber type of material in which, the liquid electrolytes have to flow through. And it plays many, many important roles, right? So it provides surfaces for electrochemical reactions. It conducts electrons and heat. And it also needs to distribute the liquids. And so it's a pretty interesting, actually fundamental problem from the transport standpoint. And I'll talk more about electrodes today. So people are thinking about how we decrease the cost. And there is a lot of nice work lately. And there are basically, you could break it down into 4 areas. There is people who work on really the chemistry of the redox active species, and a lot of the work is now focusing on organics or even high molecular weight compounds. There's people who work on membrane, more cost-effective membranes. Can you transition from dense ion exchange membrane, which are quite expensive, into some sort of porous separator that would decrease the cost of production significantly? Other people are looking at electrolytes. Can we transition actually from aqueous media to non-aqueous media? Because the advantage of that is that your electrochemical stability window would be perhaps multiplied by 2 or 3. So there is a value there. And then other people, such as ourselves, are also thinking, and we're chemical engineers, so we think, how can we improve the reactor design? Okay, how can we improve mass transfer and kinetics so that we have better performance? And so we focus on the electrode, and we think about electrodes in sort of we break down the problem into different length scales, right? You can think about the macro scale, if you will, where you have a flow distributor here and the electrode against it, and you have to minimize pressure drop, increase utilization. If you go deeper into that, you come into this very interesting mesoscale, if you will, and the 2 previous speakers, they touch upon this. And here you have a very complicated problem because you have migration, diffusion, convection, and reactions on the surfaces. So it's a pretty complex problem to model. And so for those of you who are really interested in modeling, I think there's a lot of stuff that we can learn from the lithium-ion community, although the physics are quite different, but still on the methodologies. And finally, if you go even deeper, then you have the scale of the electrocatalysis, right? Of what is the effect of a certain functional group on the kinetics of the system, okay? So what we say here is that if we minimize area-specific resistance, we can actually reduce the cost, right? And that's why we think about electrodes for a while now. And just to build that before I start to show in results, for those of you who are not that familiar, the polarization curve is the classical footprint of your electrochemical reactor, and in particular in a flow battery. And you know that our voltage is going to deviate as we apply the current because we have certain inefficiencies or overpotentials. And we normally break it down into three groups. We talk about activation overpotential. That one is related to kinetics. So remember that we have electrochemical reactions happening on the interface between those carbon fibers and the liquid electrolyte. We also have ohmic losses, and those are related to, ionic conductivity on the electrolyte through the membrane, and also electronic resistances. And finally, and most importantly, at high currents, we see concentration polarization or concentration over potentials, because we start to deplete those active species near the surfaces of the electrodes, and therefore we see that concentration over potential, right? So we want to minimize these three, and actually electrodes will allow us to minimize these three. So a proper design of electrode is going to allow you to get to high power density. And one of the problems in the electrochemical community in general is that what we do is we take a technology that is very mature, in this case, polymer electrolyte fuel cells, and we say, okay, if a certain porous media worked in that application, why don't we just take it and we use it in another application? And that's what we have done. Over the last 10 years or so, we took this macro porous layer that has pores in the range of 10 to 200 micrometers, and we say, okay, that was functional. It has high permeability. It has good chemical durability. So why don't we use it in a flow battery? And we did, and it works. It's functional. It's a repurposed material. It gives you some performance, but we know now from experiments and theory that this is far from being an optimal material. In fact, this material was designed for fuel cells, which has nothing to do in terms of physics, right? In a fuel cell, you have oxygen gas coming from the cathode, and then you have water generated that has to go counterflow. So these materials were generated for multi-phase transport, and we're just using them here in a liquid phase transport system where there are electrochemical reactions. So it's a completely different set of materials. And so the question is, how should we be designing flow battery electrodes, right? That's the question I've been asking myself for the last 3 years or so, since I started my postdoc, and now also through my faculty post. So we think about, we're academics, and we try to break down the problem into the more fundamental aspects of it. And so the way I break down the problem is I think about how would an ideal microstructure look like, and how can we tune the surface properties to get good activity, selectivity, and durability. So these are the kind of problems we think about. So I'm going to talk for about 15 minutes or so about microstructure and what have we done in this space. So first of all, we said, look, there is very little understanding on how microstructures influence the performance. So let's try to understand first off-the-shelf materials that are available by vendors. So we go out and we buy different carbon papers, things like SGL, Torre, and Freudenberg, and we buy a cloth. The cloth is very interesting because it has this very unique structure. And now I'm going to characterize these materials using two types of techniques. First one, how does the microstructure look like? And you are all familiar with this. You can do imaging, porosymmetry. And second, how does the electrochemical properties look like? So we start with mercury intrusion, just an experimental technique to obtain a pore size distribution just by applying mercury pressure. And we're going to look at this series of material. This first one is this sort of SGL paper that has pretty high surface area because it has this flaky binder all over the place. That's sort of a conductive graphitic binder. And as you go up in the series, for example, to Torre, you see that your pore size goes from around 90 micrometers to something like 50 micrometers. If you go to Freudenberg, this one looks more like a spaghetti. So the fibers are more flexible. And this is because of the way they are produced. They are produced with hydroentangling. So they shoot water jets to sort of align these fibers and give them flexibility. This pore size is smaller, something like 20 microns or so. And we also throw in this series this carbon cloth, right? And the carbon cloth is really interesting from a transport perspective because it has this very remarked bimodal pore size distribution. And this is something that you can see by looking at the microscopy. You see that there are these big pores. In the intersection between threads, And then these are 100 microns. And you also have these small pores, which are defined in one given thread. So if you look at one thread, your pores are something like 10 microns, okay? So we have this very interesting series here where you have, monomodal pore size distribution, you could say, and then a bimodal pore size distribution, and a material that is highly organized, highly aligned. Okay, so the second experiment that you can do is to look at pressure drop. So remember that in a flow battery, you are actually flowing a liquid electrolyte with pumps through a reactor. So if your porous media has very low permeability, then your pressure drop will be very high. And that is undesirable because your overall efficiency of the process will go down, okay? So we wanted to assess that in the laboratory, and we measured pressure drop, for different materials. That's a very easy experiment. You just pump electrolyte through, and then we use certain physics, such as Darcy or Darcy-Forsheimer, to account for inertia. And we measure the pressure drop for the different electrodes. And what you see is what you would expect. Electrodes that have the smaller pore sizes have the higher pressure drop, okay? And therefore the lowest permeability. And also, interestingly, these electrodes that have bimodal pore size distribution, they feature very low pressure drop, okay? So the interesting thing here is just to say that if you compare a cloth with some of these small pore size papers, you have a factor of 3, factor of 4 difference in permeability. And of course, high permeability means low pressure drop, and that's what you want, because then you don't have pumping losses. The other part of the story is looking at the electrochemistry. And for that, we use a combination of polarization and electrochemical impedance spectroscopy. And we use a small trick to try to tease out what the mass transfer over potential looks like. And how did we do that? Well, we use this so-called single electrolyte diagnostic cell. This is a cell in which we have one single reservoir, and we flow the active species at 50% stereo charge through here, so that the molecule gets reduced, and then that goes to get oxidized. So with this cell, what we do is we have a very well-controlled state of charge, and we are basically having the same electrolyte on both the cathode and the anode. By doing so, we can actually make systematic comparison of materials. It's much more difficult, however, if you would compare an anolyte with certain vanadium species with a catholyte with other vanadium species, because each half cell will have their own kinetic constants, their own physical chemical properties, and so the analysis is very confounded. So what we did here is actually to isolate electro properties by using the same electrolyte on both sides. Together with that, we also use this so-called tempo, this nitroxyl radical, because it has very fast kinetics, okay? And so we thought that if we have a system that is very fast and very facile, then we can essentially tease out what the mass transfer or potential is. We use these laboratory cells just to give you an idea. They were developed in the Brachet lab at MIT. They are somewhere around 2.5 centimeters square. And so we ran the test, and you obtain your cell potential versus current density in the symmetric cells, and you can combine that with impedance. And then if you do your equivalent circuit or whatever, then you can extract your ohmic contribution to the overpotential, and you can ultimately calculate your IR corrected potential, right? And then when we look at the impedance, what we saw in most of the cases is that the charge transfer, so the kinetic contribution, was pretty small, okay? And most of the resistance of the system after you have corrected for ohmics is due to mass transport. So from now on, I'm going to show you a few graphs in which you will see the mass transfer over potential as a function of the current, okay? So a warm-up experiment that we can do is just to take one certain electrode, in this case the cloth, and increase the velocity, right? And as engineers, the intuition will tell us, well, if you increase the velocity of the fluid, your performance will get better and better, right? Because you have more convection, and you can replenish your electrolyte faster. And this is what happens. There's no surprise here. If you go from 0.5 to 20 centimeters per second, you see how your overpotential goes down. That's what you want. And you can verify that with your impedance analysis. But something interesting that we learned from this experiment was that at a certain point, you have diminishing returns. So even though we continue to increase the velocity, we don't really see a gain or a significant gain here. And we explain that as those being some residual kinetic losses and perhaps also some internal mass transfer, that despite of you keep pushing the system to higher velocities, your boundary layer concentration remains unaffected or nearly unaffected. The most interesting finding, in my opinion, is when we compare different papers, different electrodes, excuse me. So we fix the velocity up to 5 centimeters per second, which is quite representative. And then we compare the performance of the 4 different electrodes. And what we see is that there are actually significant differences in performance if you compare, for example, the cloth with the SGL paper. Yeah. And something like 100 millivolts, which is significant for a system that has high kinetics. And so we started to think about this and thought, well, there is something with this clothes, but it's of course not a story of about whether it's electrochemical performance or pressure drop, but it's a combination of both, okay? So what we did here is to say, okay, let's try to have some sort of metric where we can correlate the pressure drop required to pump an electrolyte through a cell as a function of the current density that you can pull out of that cell. So this is what you see in this figure. Here we have the pressure drop on the y-axis, and on the x-axis we have the current density that we were able to pull out of the cell if our overpotential is kept to 50 millivolts, okay? And what we see is really interesting. First of all, the woven electrodes, these carbon cloths, outperform all the other materials, okay? So you can get high currents at low pressure drops. And the second interesting thing that we saw is that all these, anisotropically organized papers, they kind of collapse over the same trend in which you get moderate current density, but rather high pressure drop. So there is certainly something with these woven electrodes. And at the time, we attributed it to hierarchical organization. So we say, look, there seems to be a pretty clear preferential alignment. You have this family of 2 types of pores. And so you might want to have some sort of convective transport through the big holes, and then some sort of diffusive transport through the small pores. So that was the theory at the time, but that seemed to be a little bit shaky. And so we were lucky to collaborate with our colleagues at University of Surrey, so Duo and Kion, who did a great work and also Imperial College, in which we basically took 3D scans of the dry structures, and you guys have presented a beautiful tomography data already today. So we take the images of the fibers, and then our colleagues imported that into a lattice Boltzmann simulation modeling that actually included electrochemical reactions on the surfaces, right? And they only had one fitting parameter, which was the mass transfer coefficient near the boundary layer. And they were able to actually track the experimental data rather well for the different material microstructures. And one of the conclusions of this theoretical study was that, in fact, having materials which are poorly organized, such as the SGL, for example, results in bad performance. And the reason for it, we think, is that, well, you have these parts here which are stagnant. The fluid velocity is very low. And you have these other parts in which the fluid velocity is very high. And therefore, you could imagine that the concentration over these areas is very high. There is essentially no conversion. And here, the conversion is complete. And what that means at the end of the day is that you have a very poor electrode utilization, right? So if you think about the area or the volume of your reactor, there are big areas that are underutilized. This doesn't happen that much in terms of cloths, because now you have these aligned fibers. If you look at each thread and this material is compressed, then you're basically forcing the fluid to be flowing.
I think, Mark?
Aligned.
Yes.
Hello?
Antoni? Yes,
Yeah.
we lost you for a minute, but now it's fine. Yeah.
Okay, you can hear me again and see my screen.
Yes.
Okay, so yeah, I was talking about the findings of the theory, and what we saw is that indeed, if you go to poorly organized microstructures, such as the SGL, for example, you will have these areas of a stagnant fluid. So here the velocity is nearly 0. And as a consequence, your concentration would be also, or your conversion would be nearly 100%. Okay, so this is an overutilized part of your electrode, and then you have some underutilized areas of your electrode. So that is undesired, and having organized electrodes such as cloths seem to solve that problem, at least partially. And that is something that we learned from this collaborative work with Surrey and Imperial. Now, we got very motivated about about cloths, and we basically went on and talked to UpCarb. UpCarb is a company in Massachusetts, in Lowell, where they could make and provide us with many different types of patterns, weave patterns, different alignment of the fibers. And we were curious as chemical engineers, how do these different weave patterns influence the mass transfer coefficients and ultimately the performance? And there is a publication by Kevin Tenney, who is a PhD student in the Brashet group. I have a picture here of Kevin, who did a fantastic job, and his paper got published recently. I don't have time to go into the depth, but suffice to say that cloth electrodes are really interesting, and there is a lot of actual engineering in terms of the world of textiles that could be repurposed to this application now. So a lot of interesting science could appear with these woven electrodes. And second is looking at the future, and this is some of the work that is going on in my lab now, is can we actually go to the lab and with what we've learned now from commercial materials and models, can we make an electrode from the bottom up that have the properties that we're looking for? Can we tune the pore size with precision? Can we have bimodal or even trimodal pore size distributions? Can we change the porosity gradients across the thickness? And these are the type of questions that we ask ourselves. And we just came up with a method, and this is unpublished data that we are about to submit on a new concept in which we basically make electron microstructures from the bottom up with a very facile methodology. And you end up having these structures which are highly porous, highly interconnected, and they have this very interesting bimodality where you have these sort of highways for the fluid. And then in between these highways, you have this very small porosity. So we've been working for this for a couple of years. And we've applied for a patent recently, and hopefully the paper will come out soon. And what we got excited about is that these materials actually have very good performance. There is a lot to be optimized, a lot to be understood. But we always use fibrous electrodes because they are there. You can buy them. They are robust mechanically, but to me, it still comes to the question of, are they the best option that we have? Fibrous electrodes doesn't have very high surface area, and it might be that they don't even offer optimal mass transfer for such an application. So these are the kind of problems that we're working on now, and more will come over the next months or so. And this is work that Remy, my student at TUE, and Charles are doing collaboratively in a very nice way. So we're excited about this work. Okay, so with that, I close my microstructure story. And I would like to spend the last 15 minutes, if I still have 15 minutes, Alejandro, to talk about surface.
You have, yes.
Okay, thank you. And so we're talking about surface properties now. And, in the flow battery literature, there are hundreds of papers on functionalizing surfaces. And it's the short route, right? You buy a commercial material, you make a certain treatment to it, and it improves the performance. And that is great, but we need to understand fundamentally what is going on. And that's what I'm trying to go after in this second story. So first of all, the number one pre-treatment in the world is thermal treatments, okay? Everybody's doing thermal treatments, also in industry. You can even buy now pre-treated electrodes. And the story is very simple. You put it in the oven with air at 500 degrees or so, and the performance improves, you're happy, and you use it, okay? There are many, many papers, but still it remains, but by many groups, it remains a question whether the reason for the improvement is the oxygen content, whether the reason for the improvement is the hydrophilicity. It's not clear why, okay? And so we enter this field, and we also, we've been struggling also to understand that, because it's very difficult to change one property without changing three other properties. But I will make an attempt here to understanding a little bit more about thermal treatments. So we're going to look at hydrophilicity, surface area, and functionalization. Which of these three is actually playing a key role? Is it all of them? How do they change in relation to each other? That's the story. And so we chose thermal treatments because here you have a very easy handle. You can change between temperatures between 200 and 500 degrees, and authors have reported very significant changes in cell resistance. So for this study, we chose to focus on 400 to 500 degrees because there was this very interesting shift between very low resistance and very high resistance. And this is work that I did together with Catherine. She took the lead in this study. She's a great scientist, a fourth-year PhD student at MIT. And so the story here was that we increase the temperature between 400 degrees and 500 degrees, and we start to track what happens with the surface chemistry, what happens with the 3D structure, what happens with the chemical composition, with wetting, with surface area, and ultimately what happens with the performance. And so I'm going to try to go systematically, parameter by parameter, and plotting the certain property X as a function of temperature, and let's see what we can learn. So first of all, if you look at just SEMs, you see that there are fibers and binders in here, okay? And what we see is that by increasing the temperature, after 450 degrees or so, you start to burn off this binder. And so the hypothesis here is that this binder is some sort of polyvinyl alcohol type of material that has lower thermal durability, and then it burns off. If you burn this off, then the mechanical properties of your electrode basically collapse, yeah? So we look at that, and we also look at the mass and the areal density, which is ultimately the mass. And what we see is that indeed, after 425, you see a huge decrease in your mass because you're burning the binder. We also look at tomography with our collaborators at PSI in Switzerland. What we saw is that indeed, as you go to higher pre-treatment temperatures, you start to see how your structure starts to collapse. So it becomes thicker and thicker because you've lost that binder that keeps things together. Give me 1 second because I'm going to charge my laptop.
We need to make better batteries.
Exactly, yeah. Maybe a flow battery for a laptop. Because I changed from this computer to the other. I forgot plugging it in. Okay, so now we look at oxygen functional groups, and we did XPS for that, and then the characterization. And what you learn from it is that the oxygen to carbon ratio increases as we increase the pretreatment temperature. And this is to be expected. You know, you expose a certain carbon material to oxygen, and the kinetics increase, and therefore you have more peroxides and hydroperoxide functional groups on the surfaces. Okay, so you know, oxygen goes up, the mass goes down. Let's see what happens with the surface area. So we measure the surface area, and we used basically capacitance measurement. So trusting that the double layer capacitance is proportional to the surface area. If you believe that assumption, then we basically see that the surface area increases a lot between 0 and 400 degrees, and then it starts to decrease, okay? And so there we thought, okay, this is decreasing because we are burning off the binder, and the binder was responsible for high surface area material. So this is an undesired outcome of thermal treatment. The other parameter that we're interested in is the wettability. So as you can imagine, this is a one-phase flow problem, and therefore you want your electrodes to wet and to basically soak in the water so that you don't have underutilized areas. So just for those of you who are not familiar, when water touches a solid surface, it can be hydrophobic, hydrophilic, or what we call spontaneous imbibition, which is just it sucks in immediately the liquid. So we make these measurements, we run these measurements, and we saw that for pristine, you have 140 degrees or so. You go to 400 degrees, then you already bring your contact angle down to 72. And for all the other temperatures, you have spontaneous imbibition. So we were happy about it. We thought, okay, it wets really well, but can we learn something else from that? And what we did there was we did dynamic wetting measurements, so that there's a lot of theory on that on surface science. And what we looked is at the speed at which the droplet expands over time. Okay, and we did that. That is in the publication. And we saw that as you go to the right in this series, then the speed of wetting goes higher and higher. And that makes sense because your intrinsic wettability is increasing as you increase the oxygen functional groups. So far, what have we learned? So we've learned that if you increase the temperature, your mass goes down, your surface area goes down, your oxygen content goes up, and your hydrophilicity goes up. Okay, but what happens with the performance? And this is the last result in this story, which is now you put it in a vanadium flow battery, a full flow battery, so a catholyte and anolyte, and what you see is that the pristine electrode has this performance, this polarization. As you increase the temperature to 400, you get a pretty significant gain in performance. And as you go higher and higher, you start to see as you have now diminishing returns. So at some point you're going up, but then there is no significant difference anymore. And when you go to 500 degrees, actually the performance goes down. So remember that at 500 degrees, your electrode had microstructurally collapsed because it doesn't have binder anymore. So in terms of power density, we thought, okay, 475 is the best. And, we're happy about that. Maybe we used it for the follow-up experiments, but we wanted to get something out of it, something more fundamental out of it. So what we did is now we take the exchange current density, that is something that you can extract from the experiments, and we plot it as a function of the pre-treatment temperature, okay? And this exchange current density is normalized by the geometric area of the cell. So it tells you something about the overall performance, but is still convoluted by the electrochemical active surface area. That if you remember, I said before that the electrochemical surface area was decreasing with the temperature. So how do we convert this exchange current density that depends on each electrode to actually something that is intrinsic to a certain material? And what you can do, if you use your Battle-Bulmer and your kinetic rate constant, you can actually extract out a kinetic rate constant that is normalized by surface area, okay? And what we found here is that indeed there seems to be a dependence between the oxygen to carbon ratio and the estimated rate constant, okay? And I don't want to make strong conclusions from that because there are several assumptions. You have to assume that your capacitive surface area is representative of an actual electrochemical active surface area. But we start to believe that indeed oxygen functional groups do play a role in the kinetics of those particular reactions. So that's what we learned, that there are a few properties that go up, there are other properties that go down, but the cell performance seems to find a sweet spot in between these two. And so the next question would be, can we actually achieve these desirable traits without the offsetting trend? So how do we get the best of both worlds? Yeah? And that's a bit what we are doing at the moment. So there are several research lines that we're following. One of them is in collaboration with several departments at MIT, material science and civil engineering, on looking at heteroatom content by using bio-derived sources.
We lost Antoni again, right? Yes.
To make it. Hello?
Yes, now you are back. Great.
Okay.
No problem.
Sorry, how long did you miss?
Perhaps, yes.
Previous slide or still on this slide?
In this slide, yes.
Okay, great. So I was saying that we work now on how can we get functionalization through other methods, for example, by looking at bio-derived carbon materials, or can we actually change the source of our fibers, so from PAN to pitch to other materials. And also some work that we're doing in my lab now is we're looking at polymeric redox active coatings that can be used actually to accelerate reactions or protect degradation from the electrolyte. And just these are my last two slides. One highlight, this is a paper that came out recently in which we basically used, we thought about, well, can we actually replace the source of the carbon, which is now polyacrylonitrile, to some sort of bio-derived component. And there is a lot of work in biomass-derived electrodes. I'm sure you're familiar with it. And the goal of this study was to try to have some correlation between the functional groups and performance. And to do so, we picked two sources. So one is lignin and one is chitin. And the reason why we chose chitin is because it's rich in nitrogen and oxygen. So that is something that is interesting just to see if that can accelerate kinetics. And in the other case, is rich on oxygen. So we did that, and then we selected, this is work that Charles Wan did, a PhD student in the Russian lab, where he looked at the effect of adding chitin to an electrode that has been thermally treated. And what he sees is that there is an increase in the performance. And of course, there are several reasons for it. One of them is that you have higher surface area, you have these small particles. And the other reason is that these nitrogen and oxygen groups seem to also play a role in the kinetics of the system. So that is another approach that folks can use to try to accelerate these reactions on the flow battery. And with that, I want to conclude. I hopefully shown you that by fundamentally understanding the role of microstructure and the role of surface properties, we can start to make better flow battery electrodes and flow battery reactors in general. And I think we are going to need bottom-up design. And that's why I really like this webinar, because I think we can learn a lot from the lithium-ion battery space that is much more mature than the flow battery space. And we can take a lot of the nice methodologies that you guys are developing, machine learning, fabrication, correlation between synthesis and structure, and bring it to the flow battery space to make an impact there. And with that, I would like to thank many people, my group, which is small. We started 1 year ago, but we're growing, and collaborators at MIT, at Surrey, at Imperial, and of course, my mentors throughout the last years, and the funding sources. And with that, I would like to thank you all for your attention.
Thank you very much, Antoni, for the great presentation. Very inspiring presentation. And definitely there is a lot of possible bridge between lithium-ion batteries and redox flow batteries. You are totally right with that. Thank you very much again. It was very nice that you accept the invitation. So I really enjoyed. So you have questions in the question session. Maybe you can pick them. You can click in the start or live answer, and then the question will appear on the window.
Yeah. Okay. So should I start with the first question? Okay. Diana.
Diana.
Okay. Hello, Diana. In terms of mass transfer in the cloths, do you think the biggest pores increases the effective diffusion coefficient of the vanadium species, while the micro nanopores increase the surface chemistry, thus improving the overall? Yeah, I think so. That's a great question. We are still trying to understand that. It's a bit hard of a problem because you have different length scales, but we believe that the large pores will serve as convective highways. They have low pressure drop, and therefore you can have high velocity. And then the fact that you have then these very narrow aligned pores, so within the alignment is very important. The fact that the fibers are aligned, then indeed you have a higher effective velocity, and therefore you have better mass transfer. So that's, yeah, you're right in your description. Yeah. Okay. So yeah, I'm curious about the degradation performance of flow batteries with different microstructure electrodes. Do you have any related? Thanks for the question. We are doing some of that work now, but we haven't done it yet. That's the honest answer. The microstructure study we did with commercial materials in organic media. So I presume there will be very different degradation mechanisms if you repeat those experiments in aqueous acidic vanadium, for example. So we haven't done it. It's really important. It should be done, but we haven't done it. Okay, so, okay. Yeah, again, will a bigger contact surface increase or decrease the degradation performance, which seems to be a huge problem? Again, I don't, what do you mean with contact surface? Do you mean contact angle? Perhaps you can clarify and then I can follow up. If you mean contact angle, I think you want to have low contact angle so that you have high wettability and high utilization. I agree with you that degradation in organic flow batteries is going to be big. I think it's going to be a big topic. We have one PhD student working on that now. And, I cannot tell you a definite answer, but if you clarify what bigger surface contact means, then we can follow up. Thanks. Eduardo, hey, many redox flow batteries increase the resistance because the electrogenerative species attached to the electrode. Do you think that the modifications in your electrodes prevent this process? Yeah, great question. I think this is particularly a problem perhaps with quinone type of flow batteries where you have indeed some degradation processes that will cover the surfaces. We're working on that again. That's what I said before. This is an unexplored territory. There is literally zero or nearly zero work on flow batteries on exploring, let's say, degradation prevention coatings. And we have some ideas. We are looking into that. I think there is a lot that can be learned from solid electrolyte interfaces in lithium-ion batteries. And I hope that we can repurpose some of those concepts for that. So far, what we've done is to use commercial materials. And for the new materials, we are now developing some conductive coatings exactly for that purpose. So if you ask me this question in a year, then maybe I have a better answer for you. David, hey, thanks. What would be, in your opinion, an optimal surface treatment in case of organics redox active molecules such as TEMPO? That is a great question that I asked myself. So let me tell you something. I think, in principle, you might not need a sophisticated pre-treatment for organic flow batteries. The reason being is that the organic electrolytes, they wet very well. Their surface tension is very low as compared to water. And because the surface tension is so low, you have full wetting, yeah? And so because you have full wetting, you are utilizing your area much better than in an aqueous flow battery. And so in terms of electrode utilization, I would say maybe we don't need to worry about that much, but we need to worry about is durability of the electrode surfaces, whether you have some degradation reactions and things like that. Furthermore, TEMPO is very fast kinetically, and therefore you don't need to have any treatment to make it faster because it's so fast anyway. You know, so surface area doesn't matter that much. That's the advantage of organic as well. Yeah, thank you. Okay, Mona Lisa. Thank you. In the slide where you mentioned the duration of the thermal treatment is 30 hours. Could you comment on why you choose 30 hours? Also, could you comment on a standard flow rate to, for example, 10 milliliters of aqueous electrolytes? Great question. Okay, so we chose 30 because there was a lot of literature on that. I know that there are some ongoing studies now on changing the time. So there you have a very nice kinetic study as well. So that is certainly very interesting and very relevant. So that hopefully answers your first question. We chose it because it was the standard literature value. And so we thought, okay, let's study the effect of temperature. Now, other groups are taking one fixed temperature and doing different times. And then you asked me about comment of a standard flow rate to flow 10 milliliters. So we also use 10 milliliters here in the lab as a side note, but your flow rate is going to depend on your reactor design, okay? So you want to have a flow rate that is going to provide you an interstitial velocity of something between 5 and 10 centimeters per second. And the interstitial velocity you can calculate approximately as the division between your flow rate and your cross section, yeah? And this depends on the flow field that you use. For example, imagine that you use a flow-through flow field, like we did. There you have a cross section, which would be the product of the electrode thickness by the flow field width, okay? So if you have a cell like ours, which is 1.6 centimeters in one direction, and the electrodes are something like 300 micrometers, then you're talking about flow rates of around something between 20 to 50 milliliters per minute, just to give you an idea. If your flow battery is bigger, then you're gonna need a higher flow rate. Otherwise, your velocity will be very slow, okay? Paul, the fluid returns to the same container before and after reaction with an electrode? Yes, but there is, keep in mind, Paul, that there is no reaction in the same sense as in a lithium-ion battery. There is no intercalation reaction whatsoever. So in an organic flow battery, in this case, I saw the TEMPO, the electrodes are there just to provide the electrons, you know, in the interface between the solid and the liquid electrolyte, and then the electrochemical reaction happens. But there is not, in principle, there is not a damage to the electrode or contamination that we have observed. Murat, you investigate the effect of annealing on the mechanical strength on the porous material. Okay, if by annealing you mean the carbonization, for example, or the thermal treatment, we have not. So we haven't done a systematic mechanical study. I wish we would have, but I just don't have the know-how nor the infrastructure to do it. I think it's important. You know, it's as important as in a flow battery, you have compression, right? You have compression of the flow fields on the electrode. So you want to be sure that your electrode can sustain that compression. and it doesn't crack when you assemble it, but we haven't done it. But I suspect, I mean, we know it now in the lab that we've seen in the lab that changing the temperature of the carbonization does play a big role in the mechanical properties. So that is an important point. Thanks for your question.
You have a comment also in the chat from Kyung Kai.
Okay, Kion. Thanks a lot, Kion. I hope I presented your work well. I'm not a modeling guy, but I try to do it as good as possible.
No, it was great presentation, Antoni. Thank you very much again. I think it's time to close this session. I mean, of today. Thank you, Antoni, again for having accepted.